Good afternoon, everybody. We'll start today a series of lectures, definitely two, maybe three, depending on us, about random matrices. So that's the topic. Properties of random matrices. Okay. What does it mean? We'll talk about square matrix. We will assume that the matrix is the elements of the matrix are random, generated from some distribution, which we'll sort of specify later on. And then we want to compute statistics of various types. The most important statistics that I'll talk about will be the properties, the statistical properties of the eigenvalues. That's 90% of what I'll talk about, or 95% what I'll talk about is about the eigenvalues. But that's not necessarily the only statistic that might be interesting. For instance, you might also ask about the eigenvectors. What can one say about the statistical properties of the eigenvectors? But as I said, let's leave it aside. So we will focus on what's called eigenvalues, but even eigenvalues. So let's be more specific. We have W, a matrix n by n. As I said, a random matrix. So you take the matrix and you compute the eigenvalues. Let's say you order them, so you have lambda 1, and I'm going to assume that it's diagonalizable, but it's not, doesn't have its pathologies. So you have lambda 1 bigger than lambda 2, up to lambda n. So I'm going to assume that there are n eigenvalues. Okay? One can ask several questions. Of course, when I generate another matrix W, those lambdas will change. And that's what I mean by statistical properties. You want to know how they change, or what are the distribution of properties. But ideally we should ask is about, even if we focus on the eigenvalues, okay, we should ask about, let's say, the probability density of lambda 1, lambda 2, up to lambda n. The probability density. So multiply by d lambda 1 up to d lambda n, integral is 1. Okay. So this will be the joint probability density of the n eigenvalues. Okay. But when I mean probability density, I mean compute this lambda for given W, generate many vectors like that, and then compute the probability.
So you said diagonalizable, but so not necessarily symmetric now?
Well, this is. Oh, sorry. Yeah, you're right. I mean, I'm assuming that's real. Okay. So if I don't do this, I don't even have to assume that they are real. They can be complex.
So just for reference.
I'm assuming. I'm assuming for. I'm assuming the matrix has n eigenvalues. Okay. Good. So even if what I'm saying is, even if we focus on only the eigenvalues, this will give us the full, in principle, the full information, statistical information about the eigenvalues. How many eigenvalues are near lambda 1, how many near lambda 2, how many lambda n. That will be the kind of the holy grail. Once we have this, we can compute all kinds of things. We can compute the joint distribution of two eigenvalues by integrating on up. Or we can ask what is the marginal distribution of one eigenvalue by integrating on the rest, and so on. So that's something that will be way more than what we need. Okay, and it's kind of cumbersome sometimes. Even if I give this, then to compute marginals on various quantities, you have to walk. Okay, the most the simplest quantity that we will be interested in is the one eigenvalue density, or not joint, probability. You have a marginalizing over all the rest. So this will be, I'll call it rho of, of lambda. Okay, and rho of lambda is the probability density or distribution, probability of of eigenvalue lambda. In other words, what is the probability of having an eigenvalue in lambda and lambda plus d lambda? So this is the you can call it the spectrum or the density of states of the matrix W. Okay. Average over the whatever the ensemble is. So most of what I'm going to talk about is about rho of lambda. Okay? Not about the joint distribution of all of them, but just what is the probability having eigenvalue in a regime lambda. Okay, so is this concept clear? Okay. So please stop me now. Okay, so that's what we're going to compute. The density of state, or density of eigenvalues. Okay. So I'm going to now restrict myself. I'm going to give you a general formalism how one goes about computing those. But first of all, I want maybe one thing to say. We'll be interested, as you see in a few minutes, about the large n limit. Okay? Because otherwise we have lambda 1, lambda 2. You take another one, if we can move around and so on. You can define it for finite n, but it is well defined, but we'll be interested in the large n limit. And I'll comment maybe about corrections and so on, but let's just talk about large n limit, and you'll see more. So we can compute this histogram for infinite n and then ask how this histogram looks when n is large. And typically the convergence to large n for the matrices I talk about is rather fast. Okay. So before doing that, I would like to give kind of a general formalism how to go about it, and then consider specific cases. But we will, even for the general formalism, for now, I'll talk about about a simple case, which is that W is real and symmetric. It can be also a Hermitian complex, but let's talk now about real and symmetric. So it means that Wij is real and it's equal to Wji for all ij, for ij, or W equal to W transpose. Okay. So this would be, this restriction would be convenient even for the general, because then it means that the eigenvalues are real. So this rho of lambda is zero support on the complex plane except for the G axis. Okay, so lambda would be real. Okay, because we know that real symmetric matrix will have all eigenvalues are real. So that's we'll for simplicity for now we'll assume that. And now how are we going to massage rho of lambda to be able to do some theory? Because we're not, you can do eigen in MATLAB and generate nice pictures and so on, but we want to understand how we want to develop tools to actually compute things. So the way, at least one method to W of lambda, where W means that it is a fixed for a given matrix. Here I said, well, I'm looking for a probability distribution. This one will be, for most of the time, will be smooth, will be continuous function of lambda, except for maybe some exceptions. But if I just take one W, there is no, just have n values, right? That's all. So this will just be defined as 1 over n times sum over I goes from 1 to n of delta lambda minus lambda I. Well, lambda I are the eigenvalues of the matrix. Okay? That's the formal way of saying that this matrix W has n eigenvalues lambda I. So that there is no continuous time, there's nothing. N discrete delta functions. Delta function is discrete points. Okay, but this kind of representation will help when we go to this. So rho of lambda, we can already say that what we will be interested is in rho of lambda, which will be the average of rho W of lambda, where the average is of W, right? That's what we want. Okay, so that's. But before doing this, let's continue with this representation. This average is horrible if I just do it directly on this, because the eigenvalues are horrible, nonlinear functions of all the elements of the matrix. So there is no simple way of averaging over this thing, because this lambda I of W is horrible. It's an random variable, but it's horrible. Horrible function of the elements of W. So that's not good. We want to represent this rho with something that will be more convenient to average. Okay, so I'm going to introduce something which is a representation which is very very common. I mean, in physics, in many courses we learn it, we used it. I just discovered that it's called Sopotski's formula. I didn't know that it has a name, but now with Wikipedia, everything has a name. So Sopotsky. Formula. Okay. So what it is the following. Suppose I'm looking at something, I'm interested in 1 over x minus I epsilon. This is a function of x. And I'm interested in the limit of epsilon goes to 0. 0 from the positive side. So epsilon is positive, it goes to 0, I'm interested in this function. Okay, now of course this function will, when epsilon goes to 0, it has a very strong singularity at the origin. But I want kind of to massage to kind of identify the nature of this singularity. Okay, so it turns out that Sopotski formula is that this equal to 1 over the limit 1 over x called the principal value PV of 1 over x. I'll explain in a minute what it is, but anyway, this is the real thing. And then plus I times pi times delta of x. Okay, so both things look like singular at x equal to 0, but it's different singular. The real part is just 1 over x. But the reason why it's called principal value, we're thinking about this as inside an integral. So what we really mean is that if you have some well-defined, well-behaved function, any well-behaved function that well-behaves in the origin and so on, converges, and we're looking at this integral from minus infinity to plus infinity of some arbitrary function f of x, where So the real part will just be the integral dx f of x over x, but the principal part of the integral, which means that you take the integral outside epsilon or some cutoff and you take the limit of epsilon goes to 0. So that's what it means, what it means the principal value. So these integrals usually will converge because even if, because the singularity 1 over x will have one sign for positive x and different sign for negative x, and these two will exactly cancel each other. So if you are careful to have the boundaries kind of equal, minus epsilon and epsilon, then the singularity will cancel. So this is what it means, principal value. Under the integral, it gives you something which is well-defined.
This is the principal value of f? What you expression there?
Yeah, this is principal value of this. It means that under the integral, if you take any f, no, this is principal value of this function, which means that this is principal value of an integral of any f divided by x. If you are careful about the boundaries of this integral, you will get a well-defined answer. Okay. I don't want to get into more details about that because you can look at it in elementary textbooks of calculus. For me, what's important is that this is real. Okay? I'm more interested in the imaginary part. Okay, so now let's look about this. So this is what is the imaginary part. So if I look at the imaginary part of 1 over x minus I epsilon, I can write it as x squared plus epsilon squared, and then I'll have here x plus I epsilon, so the imaginary part will just be epsilon on top. So that's the imaginary part of this part. And now you can see why that's a delta function, because this, as epsilon goes to 0, the denominator, it diverges like 1 over epsilon. But on the other hand, the integral is finite. Actually, the integral is pi. So this function is really acting like, in the limit, like pi times delta function. Okay, so this is why in the limit of epsilon goes to 0, you get just I pi delta. And this is the part which will be interesting to us. Okay? Is this argument? Okay, this integral, this is a function which kind of has a peak, divergent peak at the origin, but the integral is finite, and the integral is in this case is pi. So again, in this case, you will get this one, and then you will get plus I pi times f of 0, because this will be like a delta function. So a delta function times f, the integral of f of 0. Okay, so that's the formula. Okay? Why this is good for us? Because it means that, and this is a common trick in many theoretical works, is to, instead of representing a delta function, to represent the delta function of x by 1 over x. Okay? So I can write down that rho w of x equal to 1 over pi n times the limit of epsilon goes to 0 of a function which I call g w of x minus I epsilon, where g w of x is sum over I goes from 1 to n of 1 over x minus I epsilon minus I use lambda, sorry, lambda here and lambda here, and this will be lambda minus lambda I. so there is no I epsilon. So this is, yeah, lambda of some function of x. Right? Here I put explicitly the x to be lambda minus I epsilon. All right, so this is kind of a Green's function, has many physical interpretation, which we may mention later on, or may not, depending how much we will be able to cover. But so now I'm going from sum of delta functions to sum of a 1 over x minus I epsilon. Yes.
Why is that to take on the
Yeah,
imaginary part?
just the,
What's the question?
So you have to take the imaginary part of g.
Oh, I'm sorry. Of course you mentioned it. Oh, crucial, otherwise extremely crucial. Okay. Imaginary part, of course. Okay, very good. So, why this is good? It still seems to be horrible because I have lambda I to average, so I'm still in trouble. However, this is, I can write this. This is something which I can write as 1 over n times trace of the matrix xi minus w inverse. So the trace is diagonal, but the trace is invariant under orthogonal transformation. So it's, I can use the representation that W is diagonal and it is this, and therefore I can write it in terms of the matrix W. But that's already a big improvement because now I have W. W presumably has some relatively simple random statistical properties rather than this lambda I. So I don't have, I can forget about lambda I. Now I have the matrix W. But the price is that I have to work with matrices. That's fine. Okay? So that's the question.
how did you get the trace?
The trace is the sum over the diagonal elements of this matrix. But the trace, the sum of the diagonal elements is independent of the coordinates. So I can take this matrix, rotate it to the eigenvector axis. Then in that basis, W is diagonal, and the diagonal is x minus lambda I, which is here. And the trace is invariant under, this is true whatever representation I use. The trace is invariant under rotation. Okay? So if this is true in the basis where W is diagonal, this is true for any basis. Okay? But now this is an inverse of a matrix. I have to invert the matrix and take the diagonal of that and sum the trace. More questions? Okay? Good. So now we are almost done because it's actually more convenient to look at the to not use W at G directly, but to use another function which is phi out of x, and G will be the derivative of phi. And it has, again, physical interpretation in terms of Coulomb force, and this is potential, and we'll come to this maybe later on, but for now, it's just a mathematical trick. So, trace of an inverse of a matrix is the same as, is equal to the derivative of the log of the determinant of the matrix. Right? A scalar, like a scalar, 1 over x, is the derivative of log of x. This also holds to square symmetric matrices. So I can write also.
So there's no minus sign like potential and force?
Well, the minus sign must be here. That is always worried about the minus sign. Okay, so sorry that same as ddx times phi, and I'm going to tell you what phi is, like 1 over n times the log over the determinant of I minus w, of xi minus w. If you take a square matrix, symmetric square matrix, take a derivative with respect to x, you get 1 over x, or the trace of 1 over x. And again, that's a classical result in matrix derivations. You learn it in various places. So I won't prove it. I won't bother to prove it. Okay? Good. So now we have log determinant. This is our phi. This is our phi here. Log of determinant of this ix minus w. Okay, so now I'm going to do the following. Okay, so we can write down that rho of lambda then, to summarize, will be ddx. Will have various limits, like n goes to infinity limit, epsilon goes to 0 plus limit, and the imaginary part of 1 over pi n of log of the determinant of lambda minus I epsilon, that's our x, times I, minus w, and now I have to average this over w. This is this square bracket. Square brackets means average over w. Okay? That's so far, I mean, okay, I'm not going to, nothing with, okay, that's quite general, right? W is a symmetric isometrics, means symmetric isometrics. I can now make one more step, which is general, which is to use replica theory. Because I have your log of the determinant, I have to average over log. It turns out that to average over the determinant is actually not difficult. Okay? So why it is so? So let's look at determinant of the matrix to the power minus 1/2. The determinant of the matrix to the power minus 1/2. This is equal to a Gaussian integral over ui over n Gaussian variables, but the measure is e to the minus 1/2 sum over I and j ui mij uj. Again, n is symmetric, and this is true for m positive definite. Otherwise, things may blow up in this interval. But if m is positive definite, it's not our W. Our W, I didn't say that it's positive definite, that maybe negative eigenvalues and so on. But if m is, here I'm talking about m which is positive definite, this is inequality. This is equality, right? It's the same as, if there was a sigma, the scalar, then you just get the 1 over the width, square root of the line. So this is like the extension of that to n terms. You can imagine diagonalizing this, and if you diagonalize this, you have product over the 1 over, the 1 over the 1 of square root of each of the eigenvalues, and the product is a determinant.
So I think if I goes for the should be after index I, please?
After index I,
No, index I in the sum and also in the multiplication.
no, this product is over the case.
Can you say that again, not diagonalizing?
With n input, what?
Can you say that again, not
So
diagonalizing?
where this is coming, so imagine I have a scalar. Imagine I have just du over square root of 2 pi e to the minus 1/2 u square now this one, you can look at the orthogonal basis, so this is diagonal, and then you have in this new basis, this is diagonal, so just a product of u squared times the eigenvalue square of m, and therefore you have a product of this square root of eigenvalues, but the product of eigenvalues is a determinant. I mean, again, if methods 1, 2, 3, whatever, you learn it, I'm sure. Okay, but if not, then we can discuss it in the break. This is for m positive symmetric and positive definite, otherwise the integrals may not be well defined. Okay. So, now you can see why this is now helpful for us, because I'm going to use this as m, right? And I'm going to assume it is positive definite, and it doesn't blow up. And that's something we have to be more careful, because as I said, W itself has negative eigenvalues, lambda, but it has to do with going into the complex plane and making sure everything is all right, kosher. I'm not going to do this in the original research article. You will find more careful. And I'm going to assume, I'm going just to give you how the recipe of how to work and hope that things don't break through. Okay? So I'm going to assume that this is kind of all these relevant integrals are well defined. Okay, that's maybe one needs to go to lambda and to u and to integrate over compute, but we will not worry about it. Okay. So, but we have to average. I don't want to use this because I want to average the log. So I'm going to use determinant to the power. Okay, so again, so log determinant of m to the minus 1/2, which is here, is determinant minus 1/2. I want to, instead of the log, I want to use determinant m to the minus 1/2 to the power of little n minus 1 and take the limit, n goes to 0. That's our famous replica. Okay, so another way of saying it is already discussed in the previous lecture. You can also write it as dn of this one, of z to the n, zn, where zn is this quantity. So now if we want to average, okay, before averaging, so, okay. Okay, so that's fine? Okay. Now, okay, what we are interested in the log determinant, but that's fine, because this one is just minus 1/2 log of determinant of n. So we shouldn't worry about the minus 1/2. We're interested in the log of determinant of m. This will be our m. But because of the log, this is the same as minus 1/2 log of determinant of m. So that's fine. So I can just multiply by 2, minus 2. And then I have to use replica to go to the power n. Okay, so the upshot of all this is that I can write down now what is what we need. We need then the average of the log over the determinant, average of the log of the determinant of our matrix lambda minus I epsilon I minus W. We're going to use this to average over this. We're going to multiply by, okay, this one. Instead of using this, I want to use minus 1/2 to relate it to the Gaussian variable. So I'll get minus factor minus 2 here, and then have here minus 1/2, which is fine. So that's what I want. But basically, this I can write down as minus 2 times ddn in the limit of n goes to 0 over the determinant lambda minus I epsilon I minus W to the power minus n over 2 of the major, in the limit of n goes to 0. Okay, so we have several limits. We have large n, we have epsilon goes to 0 here, and now we have this replica n goes to 0. Okay, fine, but that's our partition function to the power n, basically. So how do we deal with this? What is this determinant? And then we want to average this. Okay? How we deal with this? Well, the same trick as the replica is that we, instead of having, if we want to have this to the power n, we just take this to the power n. Okay? So we replicate this interval. So basically, you see what's going on here is that our problem of eigenvalue spectrum is intimately related to a statistical mechanics of a Gaussian variable. That's kind of where the n here, kind of energy function, so to speak, is given by this lambda I minus W. And because of the averaging, we want to take this partition function to the power n, we just replicate it. Okay? So this quantity which we have here, we will just use inside this bracket, will be the following, will be pi, alpha goes from 1 to n, of du alpha, again from minus infinity to plus, this is n-dimensional interval. We'll have our measure e to the minus 1/2, sum over alpha goes from 1 to n of u alpha dot u alpha. That's this term. No, I'm sorry. I'm now putting n. This is now n. So this will be lambda minus I epsilon. So this will be, the diagonal term will be minus lambda minus I epsilon over 2 over the sum. And then there is W, so this is plus 1/2 sum over alpha goes from 1 to n of u alpha dot W u beta. Okay, I just put n inside, and again, like in the spin glass, it does not replicate. W is the same W, only the statistical variables, only the Gaussian variables u are replicated. So W remains the same, and now we can basically head here into this and average this over W. This does not become W, right? So basically, we can summarize it and say that our quantity of interest, if I call it again a replicated partition function, again there are 2 pi, doesn't matter, will be given by this new statistical mechanics problems where I have n times little n intervals from minus infinity to plus infinity. I have a diagonal term minus lambda minus I epsilon over 2, sum over alpha goes from 1 to n of u alpha dot u alpha plus the log over the average over W over this term of exponential e to the 1/2 sum over alpha from 1 to n of u alpha dot W times u beta, and average over W. Okay? So this part here is quite general in the sense that I didn't assume anything about this particular statistics of W, only that it's real and symmetric, so lambda is real. Okay? So then Gn is a function of lambda, of course, and we'll have to take a derivative with respect to lambda in order to get G and the imaginary part and so on and so forth.
matrix with the replica matrix? How can we have beta?
Ah, sorry, no, there's no beta here, it's alpha. Ah,
Also in the line above.
also where?
Right part of the line above. The right
Oh,
most.
here, right. Thank you. Okay. And now you see that this now what I said until now, it's general. I didn't specify any example of random symmetric matrices, real matrices that you have, you can use this formula. Itamari model.
No, I was convinced there was a beta, but now when you dropped it.
No. This is U alpha. This is U alpha, W U alpha. There is no beta. Just replicate it.
So the power little n is over the determinant, not the.
What is little n?
In one line.
This sum here or this
No.
here?
Yeah. So you have the power of.
No. The matrix to the power minus n. It is like n here, but no, you're right. I'm sorry. Yeah, the determinant, right. Sorry. This is the determinant. Minus 1/2. The determinant. You're right. Thank you. Determinant to the power. What?
No, the one minus what happens on the matrix.
Determinant minus 1/2 is this one. And I'm replicating it n times.
Yeah.
So I take this quantity to the power n. Right. Thank you. This is where I get it. Thank you. Now, with respect to the question of Itamar, the coupling between replica will come by averaging. After averaging, this will be a mess here. And there will be a replica coupled. But before averaging, there is no coupling. So the log of this, of the average of this, will have, in principle, all kinds of very weird and problematic things. But until now, the point is, until now here, it is exact. Okay. So now I want to apply it. Well, we're going to apply it to several cases, but some of them in the class, some of them in classroom, some of them in homework. But I want to apply to derive perhaps the most famous and simplest result about the spectrum of eigenvalues of a random matrix. So until now it's general. W is whatever it is. And now we're going to assume that W ij, for let's say I less than j, is all of them are IID with zero mean. So Wij, all of them are zero. Gaussian. They are Gaussian. First moment is zero, and the second moment is let's call it j squared over n. So all the lower triangular, for instance, are all IID with these statistics, and the upper one are, of course, determined by the symmetry, that Wij is equal to Wj. Now there is also diagonal. I'm going to ignore. This also includes diagonal, but in the large n, doesn't matter. The diagonal terms will never really play an important role. It's fine. You can include the diagonal after this. Okay, very good. So this is called Gaussian orthogonal ensemble. Let me tell you why. Because if you look at P of W, if you write the joint distribution of the entire matrix, it's just going to be e to the minus n over 2j squared, or maybe 4j squared, times sum over I and j of Wij squared. Why 4? Because I doubled the sum over less than j and larger than j, so I corrected it by 4. So this is the measure on the matrix W. defined by this, but this is also, I can write it as e to the minus n over 4j squared times trace of w squared. Symmetric, so that's like w transpose w doesn't matter. Now this measure is invariant under a rotation of w. Trace of w squared will not change under orthogonal transformation, like we discussed before. A symmetric matrix, this is a symmetric matrix, and the trace of it will be invariant if we under a change of orthogonal multiplying w by. Okay, so this is why it's called Gaussian orthogonal ensemble. Orthogonal means that the measure on W, on the matrix W, is invariant under orthogonal transformation. Okay? And this leads to, I'll already tell you the result, to Wigner, the famous physicist, theoretical physicist, Wigner's semicircle law. Well, I won't tell you, I'll keep you in suspense, but we will, at the end of the day, hopefully derive this. But this is the first and kind of the most fundamental result of random matrix theory. It's amazing that one can write down explicitly the distribution of the eigenvalues. Moreover, for this, you can write down the joint distribution also, and so on. So this is the simplest example. Okay, good. Wigner didn't do it with replicas. The first one that did it with replicas is Edwards and Jones. Edwards and Jones, I think 1970 something, I think 76 maybe, I don't know. But Edwards and Jones, I'll put it in our Moodle page. A very nice and elegant derivation. Okay. So now we're going to take this and to do the average W over this particular ensemble. IID with zero mean and W. You see J squared over N again is the same as in the spin glass. This is the correct, if you want the density of if you want the eigenvalue, the density value not to blow up, not to shrink to zero, this is the correct normalization. Okay. So let's do the average. Okay, so we have to do now this average, this exponential average over W. Let me do it there. I'll do this. This will be relatively straightforward, and then after the break we'll actually solve it. But for now, let's just do this integral. So I want to do this average, this quantity here, average over W. But this I can write down explicitly as e to the 1/2 sum over alpha, sum from 1 to little n, sum over I and j of ui alpha, uj alpha times wij. Or I can get rid of the 1/2 and put I less than j. Okay? And the reason why, because each one of these are independent variable. So this is like product over I less than j of e to the sum over alpha of ui alpha, uj alpha, all this times wij. And now I want to do the average over W, but now this is product of independent functions of each one of the elements. So basically I want to average each one of these terms and take the product. But this is simple. This is just Gaussian average. Right? So this is an exponential. So this is the average is simply I less than j j square over 2n. It just averages over the Gaussian measure of wij for each element. Each element, so this is just a variance j square over n, comes here. And this I can then write back as e to the sum, because of the product, sum over ij. I'll have here j square over 4n, because I'm allowing now I equal to j. And you see in all these manipulations, I ignore I equal to j. It doesn't matter, so I enlarge n. So therefore, when I have I less than j, and I want to write just ij, I just divide by 4, and then I have u sum over alpha, sum over beta, ui alpha, ui beta, uj alpha, uj beta. And finally, this I can write as e to the n times j square over 4 times sum over alpha and beta of q alpha beta square, where q alpha beta is defined as 1 over n times sum over I from 1 to n of ui alpha, ui beta. You see, we are getting into kind of spin glass, similar to our spin glass theory. We couple the spins here. The spins are not eigenspins, but it's Gaussian ui's. But again, after averaging over the random matrix, you get this coupling between alpha and beta on a given site, and everything is square. So now, before we get into our breakdown, you see what we have here is Zn of lambda in this integral over this Gaussian variables u's times e to the minus lambda minus I epsilon over 2 sum over alpha from 1 to n of u alpha dot u alpha. And then log of this, it seems to be plus n j square over 4 log of sum over alpha beta q alpha beta square. So that's it. Now, just make sure that you understand this q is still a function of the u's, because this is our definition of q. So this q has all u's in it. But this is, put this inside here, you get a well-defined function in the exponent of everything is an exponent of the u's, and you have to integrate from 1 to infinity plus infinity, and all that. You throw away down the drain the random. Okay, now what we'll do after the break is use large n to our advantage, and of course small n goes to 0, and then basically will lead us to the solution. But let's just take a break. If you have questions, come to me now. Okay? Everything? Oh, no, of course not. Of course not. There's no log. There's no log. Okay. There is, where is it? There is this one, and log of this one is just n j square over 4. You have to be alert. On purpose, I'm making mistakes. Okay. Yes.
כאן כמו כל המוסיפים לפיצוי הזה, לערבוב,
כן.
אז יש כאן סתירה ב-x, הכוונה להוסיף כאן x, להוסיף את הסתירה בזמן.
זה קוראים ללמדה, זה על-פי למדה. זה על-פי למדה.
אז מותר להחליף את הגבול של...
אנחנו נחליף את כל הגבולות ברצוננו, אנחנו נעשה את הגבול, נחליף כל הגבולות. מותר, מתמטיקאים אסור להם.
מה בגלל
הביצוע כאן צריך להיות מחוץ ללוג. זה אותו ביטוי, כאילו,
בוא תסתכל אצלי, אני לא...
זה לוג של
בתוך האקספוננט.
כן, הלוג צריך להיכנס
בתוך האקספוננט
לכאן.
הראשון.
מה?
לא.
לא, אם הלוג נכנס לתוך האקספוננט אז זה מתבטל.
נכון.
זה לוג של ה...
לא,
עד כדי הלוג.
לא, זה אקספוננט.
לא.
כאן יש, אין בעיה, כאן יש מכפלה אקספוננט. בוא נסתכל רק על האיבר הזה. האיבר הזה זה אקספוננט של לוג של ה...
כן.
נכון.
הכל בסדר.
לא מבינה מה צריך את השלב הזה בכלל, אבל בסדר. זה כדי להראות שם. לא, מה שלא בסדר שזה כאן. למה הקו כאן?
לא, כל העניין.
למה?
הוא עוד מתחשב בכניסה של לוגים. לא?
לא, בסדר.
אם אתה מכניס את הלוג לתוך הזה, אז הלוג והאקספוננט יתבטלו, נכון?
כן, הלוג הזה הוא בלי...
מה יהיה עם הלוח הזה? איפה? איפה הוא נגמר כאן? חד מבחינתה. ומה שהוא ראה, מה שהוא ניסיונית, ראו ספקטרום מאוד דומה מה שציפו זה לראות ספקטרום גאוסי.
אז מה, רמות האנרגיה ממש קיבלו את
כן, אבל אני אומר, גאוסי או פרסון או משהו, הדבר הזה.
אבל ראו גם את הזנבות, לא?
לא, אז לא ראו את הזנבות, זה
זה היה חד?
מספיק חד בשביל... כן, זה היה השימוש הראשון.
אז זה אומר שזה יחסית די.
כן.
מספר, זה אומר.
כן, אז זה היה גם מספיק גדולה.
אם אתה מקבל משהו שהוא קרוב לאחד, אבל אני לא גדול, אתה מקבל משהו קרוב לאחד, אבל אתה אף פעם קורא קרוב לאחד לגבול של
זאת אומרת שאם אתה קח, זה ניסוי במטה, קח מטריצה כזאת, תסתכל על מטריצה כזאת, תסתכל על הספקטרום שלה, אבל קח חשפן, שרוב האלמנטים נוספים, אתה תראה שהחצי מעגל נמרח, איזשהו שם כמו אליפטי, זה לא, אין...
אתה אומר שבשבע?
לא, הפוך, חיים אומר שראו את זה באמת ככה, שזה ניסוי, כלומר, אתה יודע, כמה זמן מחשב, ככה ניסוי רע, ככה חשפן. אתה רואה בעין בעצם כבר אתה רואה. אתה רואה את ה...
תמיד מקבל משהו קרוב לקצה, אתה פעם רואה סוף המסך.
אתה רואה פיינל ספור.
פיינל ספור.
Okay. So we got to this point here. So we want to solve this, we want to compute this partition function. Okay? Where you have this nice term, but you have this function, quadratic function in U. Right? So this is a quadratic function in U. This is U alpha dot U beta and a Q alpha beta square. So what we can have two avenues. One avenue is to get rid of the square by Hubbard-Antonovic transformation, as we did in the case of Eigen-Stigler. We can do that. But we can also use a more general trick, which will work also if this is not necessarily a square, but some other power, which is introduce delta function. So we're going to enforce this equality by adding delta functions into it. So we're going to write this, we're going to write as integral over, so now over Q hat alpha beta, all alpha beta, and integral over Q alpha beta. Now they are now integration variables. Okay. Then we have, but Q hat and Q are kind of conjugate variables. So I'm going to use I and this is normalization which I like. Sum over alpha beta Q hat alpha beta Q alpha beta. Okay, I'm going to use the integral representation of a delta function. So delta function is dk over 2 pi e to the I kx. So k is q hat and x is q, or delta x minus a minus I ka. So k is our q hat and x is our q and a is this one. And I'm adding an overall normalization factor for convenience. Not important. So then I have here, well, I can also now put this plus n j square over 4 times sum over alpha beta q alpha beta square, and pulling this out of any u integral, And this equality will be enforced by the integral over q hat, like here, by the integral over k. So k here is q hat. So this part, then I have times the integral over u alpha, and I have two terms. I have one term, the original term, minus lambda I epsilon over 2 times sum over alpha from 1 to n u alpha dot u beta, dot u alpha. That's the original term. And then from the delta function term, I have minus I n over 2 sum over alpha beta q hat alpha beta u alpha dot u beta. And the n drops because this is one of the n. Right, so this term, think about this term together with this term is imposing the delta function, imposing q alpha beta being equal to this. This is the combination of these two terms. Q hat q minus q hat times this means that q has to be this. Okay, so this now is the same as this, but I enforce this equality by having now two integrals. Okay? Good. So, but now we are in business here because q now and q hat is not, doesn't depend on u, so now everything is quadratic in u, and moreover it is ui. So I have I integrals, okay, over this vector u, so I can write it. So the integral over u I can write as I have n of them, so each one of them is a Gaussian integral. So each one of them is the integral dx times e to the ax, which is again to ax squared, or minus ax squared. So we know it is just log minus 1/2 log of a, right? So this integral is just a to the minus 1/2. Okay, so in the matrix now, this will be, instead of a to the minus 1/2, it will be a determinant to the power minus 1/2 of the matrix here's the matrix lambda minus I epsilon I plus in my notes I wrote minus, so I put minus here to conform to my notes, minus I u hat, the determinant of this, to the power of minus 1/2, and to the power n. Okay? Look, there is a coupling between alpha and beta, but there is no coupling between different sides. So this decouples into integral over one side to the power n. Integral over one side has coupling between different replicas. So you have some Gaussian, minus xt times matrix x is just the determinant to the power minus 1/2 of n, as we discussed before. So that's what I have here, the n times. Okay? This matrix now here, this is a matrix. What is the dimensionality of this matrix? Small n by small n. Right? Each one of these terms is just integral of the yi1 to yin, where n is the replica. Okay? So this matrix here, coming from here, diagonal, from here, not diagonal, it's an n by n matrix, little n by little n matrix. Take the determinant of that to the power minus n. Okay? So we are basically done because Gn, then lambda, is this integral over q hat matrix integral of a full matrix. Now we have here several terms, minus I n over 2, sum over alpha beta q alpha beta q hat alpha beta. We have n j square over 4 sum q alpha beta square. And then we have minus n over 2 times log over the determinant of this matrix. Lambda minus I epsilon I minus q hat. And little n by little n matrix. I just exponentiated this, so it's minus n over 2 times the log of this. So now there is no u, we have only these integrals. And as we discussed in the case of spin class, now we take the large n limit. The large n limit will be controlled by the saddle point of this as a function of q and q hat. And you can forget about this integral. Okay? So now we take the large n limit. So we don't need the integrals, we just have Zn, and whatever is there, e to the minus I n over 2 sum q hat alpha beta q alpha beta plus n j square over 4 sum over alpha beta q alpha beta square minus n over 2 log determinant lambda minus I epsilon I minus q hat. By the way, there is minus I q hat. Big I here. I q hat. Okay. So, and q and q hat are determined by the saddle point equations. So we have to take derivative dZn dq and derivative of dZn dq hat alpha beta and takes to 0. So we can now write down these equations, but it's more convenient to already jump ahead and make the assumption that of replica symmetry. So we're going to make replica symmetric ansatz. Again, the ansatz is not about the integral, it's about the saddle point. The integral don't have any symmetry, like in the spin class. But once the integrals are dominated by the saddle point, there is a replica symmetric saddle point, but in virtue of the fact that this is symmetric invariant under the permutation of the alpha. So therefore there is a replica symmetric saddle point. And let me then assume it. So what is the replica symmetric structure will be? Q alpha beta will assume has a diagonal term, which I'll call Q, okay. And then off diagonal term, well, sometimes anyway, in my notes, okay, I'll call it Q0 because otherwise okay, times delta alpha beta plus Q, right? So the matrix has, on the diagonal has Q0, and all the off diagonal and all the off diagonal are Q, right? That's what's written here. So the matrix has Q0 in the diagonal and Q in the off diagonal. And similarly for Q hat, I have Q0 hat minus Q hat delta alpha beta plus Q hat. And now with this ansatz, I can compute term by term our free energy, right? What happens, what is in the argument of the exponential. Okay, and I'll give you the result, it's very simple. For instance, let's look at sum over alpha beta Q alpha beta Q hat alpha beta. So if I plug it inside this, I'll get the product of this times n, so I'll get n q0 minus q times q0 hat minus q hat. From this product, I'll get n times this, the cross terms. So I'll get n times q0 minus q times q hat plus n times q0 hat minus q hat times q, the cross term. And now this term will be q times q hat times m squared, which I neglect because I'm already thinking about n goes to 0. Okay, good. If you collect terms here, you end up with a simple guy, which is just n q0 hat minus q hat. That's this term. Similarly, q alpha beta square is n times q0 square minus q square. So these two terms are simple. Again, I'm throwing away. Okay, that's simple. The log of the determinant requires more thinking.
Why is the graphic asymmetry under? There are two terms here. More, it will be a few more about the relation between Q and Q hat.
The question is, what justifies the electrical symmetric answer?
No. It is applied twice. Once for Q and second for Q hat.
I'm just assuming the electrical symmetric says that the matrix can at best have one value on the diagonal and another value on the off diagonal. So what else can it be? That's electrical symmetric. Otherwise you will have Q12 different from Q34 or Q11 different from Q22. That's what electrical symmetric is. And similarly for Q hat. More questions? Okay, now what about the log determinant? It's a common trick. How do we compute the log determinant of this matrix? There is a Q hat matrix here. Okay, so we have to, one way is to diagonalize it. So this is fine, this is just diagonal. But what is the eigenvalues of Q hat? What are the eigenvalues of Q hat? Okay, the eigenvalues of Q hat, given this form, are two. One of them, so if Q hat has this form, right, then there are n little n eigenvalues. One eigenvalue is 1, 1, 1, 1. The eigenvector of 1, 1, 1. And this will just give n times q. Plus, q0 minus q plus n times q. So the eigenvalue will be q0 minus q plus n times q. Just sum of the rows. Q hat. Okay. Now what are the other eigenvalues? So all the other eigenvalues are eigenvalues which are orthogonal to 1, 1, 1. So the sum of these eigenvectors are 0. But if the sum of the eigenvectors is 0 and I take a matrix multiplying it by something, by a vector where the sum of the terms is 0, this will cancel. So the only thing which will remain is this.
You mean the sum of the elements of these vectors is 0?
So I'm saying that one eigenvector is 1, 1, 1, 1. If I take this matrix Q hat and multiply by 1, 1, 1, I just get Q0 hat minus Q plus n times Q hat. Okay, this will be the eigenvector times 1. This will be the eigenvector. Now if I multiply this matrix by any vector which is orthogonal to 1, 1, 1, I'll get whatever, Q, I'll get the diagonal term, it's fine, but then this one will sum to 0. It's a full matrix, that's 1, 1, 1, 1, everything is 1. and you multiply, you take a matrix, which is everything is 1, and you multiply by 1, minus 1, or whatever, something that sums to 0. So that is 0. If the sum of this element is 0, this is what the rows are doing. Take this and this, so that's 0. So you have n minus 1 degenerate eigenvalues corresponding to all the n minus 1 eigenvectors which are orthogonal to the uniform ones, and they just will have q0 hat minus q hat. This term will vanish. Again, the argument, you can think again at home. If you take a matrix like this and diagonalize it, you have one eigenvalue will be n, another eigenvalue would just be 0, because if you multiply by the orthogonal ones, you just get 0. So only all that remains is this. Okay? So with this we can now put it into the log determinant. So the log of the determinant, what we have here, we have lambda minus I epsilon I minus IQ hat. But now we know the log determinant is the sum of the log of the eigenvalue. So one eigenvalue is this, so it will be log of lambda minus I epsilon plus, minus I times Q hat, which will be Q0 hat minus Q hat. This is this, minus I and Q hat. This is the first term, the contribution from the uniform eigenvector. And then I have plus n minus 1 times the log of the other ones. But the other ones are just, I have to add just this one. Lambda minus I epsilon minus I Q0 hat minus Q hat. So that's the log of the determinant. Now I'm going to the n goes to 0 limit. Okay? And I'm expanding. So there is n here, but there is also n inside the log. So if I put here n equal to 0, I get this log, which cancels with the minus 1 log. Right? Which means that there is no order 1. The order 1 term drops. This minus 1 and this. So what we get is two contributions. One, this n times log of lambda minus I epsilon minus I Q hat minus Q hat. Q hat minus Q hat 0 minus Q hat. This is this one, the n. And from here, the expansion, which will give minus I n Q hat divided by lambda minus I epsilon minus I Q hat 0 minus Q hat. Okay, so now this is order n, the rest is order n squared. So now you see the whole free energy is nice, right? So we have, in my opinion, we can collect everything here. So now I'm looking at kind of log of this Gn. And there is capital N, I divide by capital N. And there is little n, I divide by little n. So what we have is minus I. The first term is what I wrote there. Q0 hat, here, Q0 hat Q0 minus Q hat. Then I have the same, then I have plus j squared over 4. So there is 2 here, so there is j squared over 2 of then I have from the log, I have here, plus the log of lambda minus I epsilon minus I Q0 hat minus Q hat, and then minus I Q hat divided by lambda minus I epsilon minus I Q0 hat minus Q hat. That's not bad. We have four order parameters, Q and Q0 and Q hat and Q0 hat. Two matrices collapsed into two variables, the diagonal one and the off-diagonal one for both matrices. So now I'm taking now the 7-point equation, and what we get is J square, let me just write down to you what I get if I take derivatives. So I take derivative with respect to Q hat, I take derivative with respect to Q hat 0, I'm sorry, Q hat 0. This is derivative with respect to Q and derivative with respect to Q. This is d dq and this is d dq0. These two equations, and now derivative with respect to Q hat will involve also the log. And I'll just give you the result. I Q0 equal to I divided by lambda minus I epsilon minus I Q0 hat minus Q hat, and then minus Q hat divided by lambda minus I epsilon minus I Q0 hat minus Q hat. And the second equation, IQ, so this is d dq0 hat, and this is d dq, the last one, d dq hat, IQ, rather similar looking guy, I over lambda minus I epsilon minus I Q0 hat minus Q hat. And then I have three terms here, minus Q hat divided by lambda minus I epsilon minus I Q0 hat minus Q hat. But because of this Q hat, I have another term, which is minus I divided by the same guy, minus lambda I. No, I need, sorry, here I need square. Okay, lambda I epsilon minus I Q0 hat minus Q hat, and then here square. I take, no, I take a derivative with respect to Q hat. This is not squared, but some point what is square. This is the log, here, this is the square. Here, and this is the square. Because I take a derivative with this. Okay, nothing particularly illuminating, but what is nice about these equations is that there's a very simple solution, namely all the off-diagonal elements are 0. So if you look at the solution, you get the only solution is Q0 equal to Q equal to 0. Which means that, remember, in the stimulus, the overlap between different replicas was 0 at high temperature, but then there was a phase transition where Q becomes non-zero at low temperature. But here, there is no phase transition. The system is always at high temperature. Always the off-diagonal elements are 0. So in fact, there is no coupling between. In the 7-point, there is no coupling between replicas. That's what makes it very simple. I'll talk about, hopefully, soon, if not today, tomorrow, about what is the deep reason why there is no phase transition, why there is no freezing. But nevertheless, this is the case. And if you put this,
How do you mean Q hat equals Q?
no, I'm sorry, I'm sorry, all the off-diagonal.
Yeah.
Thank you. Q hat, thank you. Q hat and Q, all the off-diagonal. And then you get J0 square Q0 is I Q0 hat for the diagonal element. And finally, if you put it, you get this equation I Q0, no, zero equals to 1 over x minus I epsilon minus j squared q 0. This is the final equation. The rest, okay.
Hi.
Yeah.
You say something about, so in the ST model it was clear what is the Q, the overlap between the two solutions.
This is the overlap. Now it's the overlap between two different replicas.
Yeah, but in the ST model it was clear what.
In the what?
In the ST model.
It is the same here. You think about the U's are, well, the U's have, I forgot to look at it. I'm not forgot, but I erased. We had a statistical mechanical problem on the U's. There was integrals over the U's times some Hamiltonian of the U's, of the U alphas. It's the same thing, except that the U's are not spin line, are not Eigen. They are, and they have this funny lambda minus I epsilon. But formally, you know, forgetting about the fact that there is this minus I epsilon, formally it is the same story. You have now Gaussian, the replicator. You know, we started with, it's the same story. We started with the U's, which has some random W coupling, and then we integrated to get the replicated Hamiltonian of the U's. The interpretation is the same. If this was not zero, it means that there is kind of freezing, that the UI average over this Gaussian measure square, and then average over W would be non-zero. If this was not zero. Okay? The U's are basically thermal stochastic variables, so with a Gibbs distribution, which originally is random, but after integrated, it's kind of replicated coupling, but the interpretation is the same. Okay, so this is much simpler than spin glass. It's not only that replica symmetric 6 points is enough, but even it's like there's no freezing, there's no, the high temperature phase is the one which is relevant. So in other words, there is no coupling at the saddle point. There is no coupling between different saddles. And the interpretation again is that there is no, that average of a U before even J is zero, and that's it. Okay, but again, this is true in the large N. I mean, if you calculate it for finite N, of course there is coupling and nothing is zero, but we're talking about the saddle point. Okay. Now again, one can do it. One can, you know, one can go back to this W before averaging and really do expansion and convince oneself that this U, this Edwards-Anderson order parameter for U is order of 1 over N. It's not zero, but it's small. So the large N. Okay. So so we have to solve this, but what about our what we're interested in, the rho of lambda? Okay, so if you go back to our expressions, remember we have to take this and we have to take a derivative. Where am I now? So Q hat is 0, right? And so this drops, and we have and Q hat here is 0, and if you plug everything, I'll leave it to your exercise, you find a very simple result that rho lambda is 1 over pi times limit of epsilon goes to 0 plus times the imaginary part of Q0. Very neat. So remember, Q0 is the same replicas. It's basically the variance, right? Ui squared. This is Q0. It's just the variance of the U's, right? It's the alpha alpha, right? So it's just the variance. Okay? And basically the imaginary part of this variance is this is simply putting this solution you get 1 over this, but 1 over this is 1 over this is q0. Sorry, lambda. Right. But by the time you take a derivative with respect to lambda, you only have a derivative here, and you get this, and therefore you just get q0. What is the question?
Some, just the notation x and lambda.
Yeah, because I use my notes in x and then decide to go to lambda. But I think now it's fine. Lambda. Okay. So
And also, maybe there's a more is about minus sign.
I don't think so.
In the,
This is
no,
correct.
in the log. But I'll look at it again, I'm not sure.
Here. No, this comes with a minus. No, I think. So anyway, if there is, but there is 2. Because I had here I over 2, so there is a factor of 2.
Factor of 2 over
And, right, and there is a factor of 2 here because of log determinant. Right, and there is a factor of 2 here. But then these equations are right. The factor of 2 goes. Okay, and here there is no factor of 2 because remember there was this square root of, minus 1, the determinant to the power minus 1/2. We want to get rid of it, so we have multiplied by 2. So this is why factor of 2 drops in this. This I think is correct, these 2 equations. Okay, so now you're almost at the end of the drama, which is how do we get imaginary part for Q0? It turns out that you can forget about I epsilon. We just solve this equation with I epsilon 0. So we get Q0 times lambda minus J0 Q0 equals to 1. Quadratic equation for Q0. And what you get is Q0 equals to lambda plus minus lambda squared minus 4j squared over 2j squared. Now you see what's going on. If lambda is bigger in magnitude than 2j, this is real, and there is no imaginary part of Q0. Now you can say, well, but what about epsilon? The problem is that I epsilon will give you an imaginary part which is proportional to epsilon. So in the limit, it will not continue. So we need really Q0 to have an imaginary part. Okay, and Q0 doesn't have an imaginary part if lambda is bigger in magnitude than 2j. But if lambda is less, it's within minus 2j and plus 2j, this is the imaginary part. I mean, taking minus 1 outside, and this is rho of lambda. So we can then conclude that the density of eigenvalues of lambda is 1 over 4j, 1 over 2 pi j squared, square root of 4j squared minus lambda squared for lambda bigger than minus 2j and less than 2j, and then 0 if lambda is outside this regime. And if you plot it, you can see that this has the shape of a semicircle. If I plot rho of lambda, function of x, 0, there is a finite band between minus 2j and plus 2j, and there is kind of square root, it's like half a circle. Well, except that I'm not good in drawing. So that's, okay, so this is the famous Wigner's semicircle.